So in this lecture, what we're going to do is we're going to consider memory management of the computer, where we're thinking really about the management of primary memory, main memory, RAM. So we'll start off with the standard quotation, which we've had at the beginning of quite a few of the lectures, and it is really pretty straightforward. The operating system mediates access to the hardware to the many executing programs so that each program executes in an illusionary sandbox. Every executing program has complete access to its own private virtualized CPU and also its own private virtualized main memory and all the other private and virtualized resources of the system. So you'll remember that one of the key ideas in this course is that every process exists in its own little bubble of delusion. And what the idea is that every process thinks that it has exclusive and absolute access to the CPU. It believes that it has exclusive and absolute access to the main memory, and it believes that it has absolute and exclusive access to any other hardware resource that might exist in the system. So of course this is entirely false. It's an illusion that is created by the work of the kernel and the other components in the operating system. And really what we have to discover is how that illusion is obtained, how it's achieved by the kernel, what the actual mechanism is for doing this. So in order to do that, in this lecture we'll explore some ancient history, and we'll look at the initial attempts going back maybe 40 or 50 years for memory management and their limitations. And once we've seen what the limitations are, we'll then look at the actual memory management technique that is used in real computer systems. Okay, so that kind of comes or is expressed as two questions. What are the issues that need to be considered in achieving a private virtualized main memory for a process? And what are the mechanisms that we can actually use to achieve a private virtualized main memory for a process? So we'll consider those in due course. But what we need to do first of all is to go back in time to a diagram that you're very familiar with from Chaos 1 and also Chaos 2. So this is our model of a simple computer. Over here we have the CPU. Over here we have the hardware main memory. And the basic idea is that the CPU is fetching, decoding and executing machine code instructions that belong to a program, and these machine code instructions are stored inside memory cells in main memory. So the key takeaway is really that we have a memory cell, an array of memory cells, a linear array of memory cells, and that each one of these memory cells contains a machine code instruction or it contains data. Another thing that's important about each memory cell is that they are the same size, and also as well that they have associated with each cell a memory address. So depending on the size of the screen that you're using to watch this, you'll see that we have for the first cell here memory address 0, for the second 1, 2, 3 and so on and so forth, all the way to the very last cell in memory, which here has the memory address 65,536. And I can see that this memory is a 16 kilobyte memory because 65,536 is equal to 2 to the power 16 minus 1. But that's really not the important point. The important point is that we have memory cells and that they have referencing addresses. So in the diagram you can see, if we examine the PC register, that the memory address that's being interacted with is address 50, and you can see that the control unit is telling the main memory that it wants to carry out a read operation. So the read operation is basically going to instruct the main memory to go to cell 50, and then whatever content is stored in that cell, well, that then has to be transferred over the memory bus and brought into the CPU. So it will be temporarily stored in the memory buffer register before eventually making its way up to the instruction register. So this is a machine code instruction rather than data. Okay, so these are the kind of key ideas. A question that then arises is this in any way realistic? And it's not, because in our computer hardware system that we can see in this figure number 1, there's only one executing process. So that's not realistic, because remember, in Chaos 2 we are studying operating systems which are multitasking, and we know that there are many processes. And then also as well, the executing process that we can see here, it's very, very simplistic. So you'll remember that the code for this program, if it was written in Java, was something like A equals 10, B equals 13, C equals 0, C equals A plus B, and then I think print C out to the screen. So that was a very, very simple program, and its memory requirements don't change. So that's really not a realistic thing. Obviously, programs, when they're executing, change, okay, in terms of their memory requirements. So if a program is, let's say for example, you have Microsoft Word open without a document active, and then you decide to load a document into Word, and that document is a very large document, then it makes sense that the overall memory requirements for Word will have to increase in order to incorporate the change in the data that Microsoft Word is processing. So our figure here isn't very accurate in regard of that. And then also as well, you'll remember that the machine code instructions that we're looking at, so for example, I'm highlighting STOD 102. We know that STOD, or we should be able to remember that STOD stands for Store Direct, and we'll also remember that 102 is not referring to an integer number that we might want to count or something like that. It is actually referring to memory address 102. So this is a physical address in the main memory. So every time a machine code instruction executes and it specifies an address, then that address in this model is physical. Okay, so that creates a problem for us because it means that this program can only sensibly execute if it is stored in this portion of memory. So I'll illustrate that in the next section of the lecture, but this is not a great way to proceed. So physical addressing, we'll see in a minute, is not the right thing to do, okay? Unless we're talking about very, very simple computers.